So let us start today's discussion. The discussion on metallurgy. As we all know, metals play a very important role in our daily life. So in depth, we discuss about the general principles of metallurgy today. Before discussing the general principles of metallurgy, first we must know the occurrence of metals. Remember, about 70% of the elements in the periodic table are metals. All such metals are broadly classified into three types. The classification of metals into three types is purely based on the standard reduction potential values. Those metals, such as alkali and alkaline earth metals, which are kept in the first and second group of the periodic table, including aluminium, which are having least standard reduction potential values, are considered as highly reactive metals. And the other group of metals, which are generally noble metals such as gold, silver, platinum, ruthenium, rhodium, osmium, iridium, etc., they are having higher E0 values and they are not good electron donors and they are good electron acceptors. Such metals are considered as noble metals, which are placed at the top of the electrochemical series, belongs to one class. In between these two, there is a group of metals which are commonly known as ordinary metals, and the standard reduction potential values of ordinary metals such as iron, cobalt, nickel, zinc, copper, etc. they lies in between the standard reduction potential values of the noble metals and highly reactive metals. Therefore, based on standard reduction potential values, the metals are classified into highly reactive metals, noble metals, and ordinary metals. And out of these three different types of metals, noble metals generally occurs in the free state, which is commonly called native state, whereas the highly reactive metals and ordinary metals, they do not occur in the free state. They always occurs in the combined state. They occurs in the combined state either in the earth crust or in the seawater. Therefore, earth crust or seawater are the two major sources of the metals. And highly reactive metals, they generally occurs as the respective halides, maybe chlorides, bromides, iodides, etc. Whereas the ordinary metals, they occurs as the oxides, sulfides, carbonates, halides, etc. based on the other element with which the metal has been combined. We used to classify the naturally occurring metallic compounds into different types. Those naturally occurring metallic compounds are commonly known as minerals. To call any substance as a mineral, it has to satisfy the following two conditions. It should occur in nature and it should contain one or the other metal. That means a naturally occurring metallic compound is called mineral, and when we try to extract a metal from a mineral, if the metal can be extracted easily and profitably, that mineral is called ore. I mean to say, all ores are minerals, but all minerals are not ores. So starting from the ore, when we want to extract a metal, we have to follow a certain steps. Those steps are generally discussed as general principles of metallurgy. General principles of metallurgy involves the following four different steps. The first one is crushing or powdering the ore. Soon after taking the ore from the earth crust or from the seawater, which is obtained in the form of blocks or rocks, it should be powdered into a fine particles. That ore can be crushed into fine particles by different methods such as ball mills or by jaw crusher, even by pulverization also. After converting the ore into a fine powder, along with ore particles, the unwanted earthy impurities which are present with the ore particles are also grounded into fine powder. Those unwanted earthy impurities are collectively called as gong, so that the powdered ore do contains ore as well as gong particles. Between these two, we need only the ore particles but not the gangue particles. So that the second step of general principles of metallurgy is the separation of gangue particles from the powdered ore. This separation of gangue particles from the powdered ore is called concentration of ore or ore dressing. So that in order to separate the gangue particles from the powdered ore, we are going to adapt a suitable method. The method which we are going to adapt for the separation of gangue particles is purely based on the nature of the ore and gangue particles, because we cannot use or adapt the same technique for the separation of gangue particles from all the ores. So there are different techniques which are used for the separation of gangue particles, out of which the first one is levication, which is also called gravity separation, which is also labeled as hydraulic washing. This method is generally applicable for the concentration of oxide ores, which are heavier than gangue particles. During this process, the powdered ore is washed with a stream of water. The lighter gangue particles are always washed away by water, whereas the denser ore particles settles to the bottom. And this method of concentration by hydraulic washing is always applied or suitable for the concentration of oxide ores which are heavier than gangue particles. Whereas the sulfide ores are concentrated by another technique called froth flotation. During this froth flotation, remember, the ore particles and the gangue particles are made to wetted by water and pine oil. The ore particles are generally wetted by pine oil, whereas gangue particles are wetted by water. I mean to say the general principle of froth flotation is difference in wetting property. The difference in wetting property is the general principle of froth flotation, whereas the difference in specific gravities between ore and gangue particles is the general principle of hydraulic washing. Whereas during froth flotation, when the powdered ore is mixed with water and pine oil, the ore particles are wetted by pine oil, whereas the gangue particles are wetted by water. When air is blown into the mixture, froth is formed, so which carries ore particles along with it, which rises to the surface. So the froth is collected and the froth is destroyed to get the concentrated ore, whereas gangue particles settles to the bottom. So then the third method of concentration is magnetic separation, where there is a difference in the magnetic properties between ore and gangue particles. Then the suitable method for the concentration of ore is magnetic separation. During the process, the powdered ore is carried by a belt which is moving over a magnetic roller. The paramagnetic particles are attracted towards the magnet and they collect very near to the magnet, whereas the non-magnetic particles are thrown away from the magnet. When these three processes becomes ineffective, then the last technique is called leaching. During the process of leaching, the powdered ore is digested or heated with a suitable solvent. The suitable solvent is one which dissolves only the ore particles but not the gangue particles. And the suitable solvent is always selected by trial and error method. When the powdered ore is digested with a suitable solvent, only the ore particle dissolves in the suitable solvent goes into solution, whereas the insoluble gangue particles are separated by filtration. The solution which contains the ore particles, from that solution, the ore particles are again separated by precipitation techniques. After the removal of gangue particles from the ore, from the concentrated ore, there are different metallurgical techniques which are available for the extraction of metal. Because as we have three different types of metals, we have three different types of metallurgical techniques, because all metals cannot be extracted by the same metallurgical technique. Generally, the noble metals are extracted by hydrometallurgy and amalgamation, whereas ordinary metals are extracted by pyrometallurgy. Where the highly reactive metals, which are having least standard reduction potential value, are always extracted by electrometallurgy, which is also called electrolytic reduction. See, under this, normally the highly reactive metals are extracted by the electrolysis of their molten metallic chlorides or molten metallic halides. When a molten metallic halide has been subjected for electrolysis by using DC, a metal ion, it moves, being a cation, it moves towards cathode, where it undergoes reduction, giving the corresponding metal. Whereas the anion moves towards anode where it undergoes oxidation, which will be liberated either in the form of a gas or in the form of a liquid. Generally, when molten sodium chloride has been subjected for electrolysis, sodium is discharged at cathode due to reduction, whereas chlorine gas is liberated at anode due to oxidation. Coming to the extraction of ordinary metals, they generally occurs either as their oxides or as their sulfides or as their carbonates like this. So for the extraction of ordinary metals, we generally use a metallurgy called pyrometallurgy. The process of extracting any metal in its molten state is called pyrometallurgy. During the pyrometallurgical technique, there are a few common operations such as roasting. The process of heating the concentrated ore in excess of air is called roasting. At the time of roasting, normally a sulfide ore is converted into oxide ore. Normally sulfide ores are subjected for roasting to convert a sulfide into oxide. If the ore is a carbonate ore, then it is generally subjected for calcination. The process of heating the concentrated ore in absence of air or in a limited supply of air is called calcination. At the time of calcination, normally a carbonate ore is converted into oxide ore. Therefore, calcination is suitable for carbonate ores, whereas roasting is suitable for sulfide ores. After roasting or calcination, we will have an oxide. That oxide has to be reduced to the respective metal by a metallurgical technique which is known as pyrometallurgy, during which smelting is the common operation. Smelting is the common operation in pyrometallurgy. The smelting is generally carried out in a different types of furnaces, out of which the more commonly used furnace is a blast furnace. The process of heating the concentrated ore along with a flux and a reducing agent in a furnace till it melts is called smelting. At the time of smelting, the flux combines with gum particles to form an easily fusible mass called slag, whereas the reducing agent is added that reduces the metallic oxide into respective metal. At the time of smelting, the more commonly used reducing agent is coke which is economical. Coke reduces most of the metallic oxides into respective metals. The role of flux in metallurgy is to convert the gum particles into an easily fusible mass called slag. Of course, there are different types of fluxes, acidic flux and basic flux. Silicon dioxide, SiO2 is an example of acidic flux, and CaCO3 is an example of basic flux, and based on the nature of the gum particles, we are going to use a suitable flux. When the gum particles are acidic in nature, then we will go for basic flux. When the gum particles are basic in nature, then we will go for acidic flux, and vice versa. Remember, at the time of smelting, whatever the reducing agent we are going to use, that cannot be selected in a blind manner. For the reduction of metallic oxide into respective metals, the reducing agent is always selected with the help of a Lingham's diagram. A Lingham's diagram is a graph which is plotted delta G naught versus temperature for the formation of different types of oxides by the combination of elements with oxygen. In a Lingham's diagram, remember, those metals which are having least standard reduction potential value, which are the good reducing agent, they are almost at the bottom of the Lingham's diagram, whereas noble metals, they are almost at the top of the Lingham's diagram, whereas the other metals, they are in between, they are placed in the middle of the Lingham's diagram. Normally, those which are placed in the bottom of the Lingham's diagram are the best reducing agents because they are the good electron donors. When we use coke as a reducing agent, of course, coke is capable of reducing many metallic oxide into respective metals at high temperature. But in two cases, we cannot use coke as a reducing agent because at high temperature, the metals like chromium and manganese, they combine with carbon, forming the respective carbide as an impurity. In such case, Normally, a carbon monoxide also serves as a reducing agent. Between coke and carbon monoxide, though both are good reducing agents, the one which can be used as a reducing agent is decided based on temperature. Below 983 Kelvin, remember, carbon monoxide will be the best reducing agent, whereas above 983 Kelvin, coke becomes the good reducing agent. When we cannot use coke as a reducing agent, normally we used to use aluminum as a reducing agent. The process in which aluminum is used as a reducing agent is called Goldsmith aluminothermite process. Whereas after the extraction of a metal by pyrometallurgy or by electrometallurgy or by hydrometallurgy, normally the hydrometallurgical technique is suitable for the extraction of noble metals which occurs in their free state or native state. The native ore of a noble metal, when crushed into a fine powder, when it is made to contact with mercury, only the noble metals dissolves in mercury, forming the respective amalgam, and the unwanted gun particles are removed, and from the amalgam the noble metals are generally separated by distillation technique, since mercury is having the low boiling point. So after extracting the different types of metals by different metallurgical techniques, the obtained metal is always impure or crude in nature. The process, by a suitable technique or by a suitable refining process, we are going to remove the impurities which are present in the impure metal in order to get a pure metal. The process of removing impurities from impure metal in order to get a pure metal is called purification of metals, which is also called refining of metals. Of course, again, refining of metals can be done by different methods. This is purely based on the difference between the metal and impurity. So the different methods which are available for the refining of metals is, first one is liquation. This liquation technique is generally used for the metals which are having low melting point, such as zinc, cadmium and mercury. So at the time of liquation, the impure metal is heated on the sloping earth of a reverberatory furnace. Since the metal is having a low melting point, it melts and flows down, the leaving behind the impurities. The second method of refining is distillation. Those which are having low boiling points are generally purified by distillation. When an impure metal along with impurities, when it is distilled, the metal which is having low boiling point distills out in the form of vapors, leaving behind the impurities in the distillation flask. Generally, mercury is purified by distillation technique. So after liquation and distillation, the third method is pooling. This pooling is a very special and a unique technique which is employed when a metal contains its own oxide as an impurity. When a metal contains its own oxide as an impurity, the metal is taken in the molten state in a furnace. When the molten metal is stirred with the freshly cut wooden poles, the wooden pole degrades, liberating hydrocarbons, which serves as a reducing agent, which reduces the metallic oxide which is present as an impurity along with the metal. So that when the metallic oxide are reduced to metal, the metal adds to the metal, whereas the impurities escapes in the form of gases. For example, when copper contains copper oxide as an impurity, that impure copper is generally purified by pooling technique. After pooling, the most important method is electrolytic refining. Remember, most of the metals are always purified by electrolytic refining. At the time of refining a metal by electrolytic method, so there are three important points. The first one is a block of impure metal is made to serve as anode. A thin sheet of same pure metal must be made to serve as cathode. A solution of soluble salt of the same metal acidified with dilute sulfuric acid is made to serve as an electrolyte. So the 3 points are very important. A block of impure metal must be made to serve as anode. A thin sheet of same pure metal must be made to serve as cathode. A solution of soluble salt of the same metal acidified with dilute sulfuric acid is made to serve as an electrolyte. For example, when we try to purify impure copper, a block of impure copper is made to serve as anode. A thin sheet of pure copper is made to serve as cathode. Copper sulfate solution acidified with 15% of sulfuric acid is made to serve as an electrolyte. Upon electrolysis, the metal dissolves from anode and deposits on cathode, leaving behind the impurities called anode mud. And this is the most important method by means of which most of the metals are purified. The other method, of course, oxidative refining. In this oxidative refining, the metal is taken in the molten state, which contains other impurities. For example, the cast iron or pig iron, which contains carbon, sulfur and phosphorus as an impurity, is purified by oxidative refining technique, during which the air is blown into the molten metal. When the air is blown into the molten metal, carbon is oxidized to carbon dioxide, sulfur is oxidized to sulfur dioxide, phosphorus is oxidized to phosphorus pentoxides, and these oxides escapes in the form of gases, leaving behind the pure metal. This is commonly called oxidative refining. The other method of refining is parting. Parting process is a very special technique which is generally employed for the removal of one metal from the other metal. For example, when silver is mixed with gold, from gold, silver is removed by parting process. At the time of parting process, remember, whatever the gold which contains a silver is digested with 30% solution of concentrate, 30% solution of nitric acid. When the gold which contains silver, when heated with the 30% nitric acid, only silver combines with nitric acid, forming silver nitrate, which goes into solution, whereas the insoluble gold can be separated by filtration. At the time of parting, if the percentage of gold is more than 30 in silver, then the nitric acid will not react with the silver. In such case, the percentage of gold is reduced by the addition of silver to the molten metal. During the parting process, when the process is carried out by using concentrated sulfuric acid instead of nitric acid, then the process is called affination. After this, there are the other methods which are also called vapor phase refining. In vapor phase refining, there are two important methods. The first one is Mann's process. This Mann's process is generally applicable for the concentration of impure nickel. During the Mann's process, impure nickel is made to react with carbon monoxide. When impure nickel is heated with carbon monoxide, only the metal combines with carbon monoxide, forming nickel tetracarbonyl as a compound which comes out in the form of vapors. The vapors of nickel tetracarbonyl on further heating, it decomposes, liberating carbon monoxide, giving pure nickel. This method of purification of nickel by reacting the impure nickel with carbon monoxide is known as vapor phase refining, which was developed by Mann's. Therefore, the process is known as Mann's process. Whereas there are another vapor phase refining technique which is called Van Arkel process. In this Van Arkel process, titanium and zirconium are generally purified by vapor phase refining. During the process, these impure zirconium and titanium are heated with iodine. Both the metals, titanium and zirconium, are converted into the respective tetrahydrides. These tetrahydrides, on further heating, decomposes, liberating iodine, giving pure zirconium and titanium. So, titanium and zirconium are purified by Van Arkel process, whereas nickel is purified by Mann's process. Van Arkel process and Mann's process, both of these two are the examples of vapor phase refining. In addition to all this, there is one more special and unique technique which is called zone melting or zone refining, which is not used for all the metals, and it is always used when the metal is required in the ultra pure form. So when we need a metal in 100% pure form to use as a semiconductor, then we will go for zone refining. The basic principle of zone refining is impurities are more soluble in the molten zone when compared to cold zone. Impurities are more soluble in hot zone compared to cold zone. By making use of this basic principle, we are going to remove the impurities in order to get an ultra pure metal or 100% pure metal, which is called zone refining. At the time of zone refining, the metal which is to be purified is taken in the form of a rod, and then a circular heater is fitted at the one end of the rod. When the circular heater is moved from one end to another end, along with the circular heater, remember, the hot zone moves from one end to another end. Along with the hot zone, the impurities are also get shifted from one end to another end. The end, which contains higher percentage of impurities, is cut and removed, and this process is repeated till we get a metal of desired degree of purity. Thank you. I hope you have understood this. If you have any doubts, please leave it in the comments.